Hi, good morning. Just recall what we have discussed in our last class. Last class we have discussed about the projection operator like E be a linear space and projection on E is a map from E to E which satisfies the condition P square equal to P. And if E1 is equal to image P and E2 equal to kernel P, then we get E equal to E1 plus E2. Okay. Now we are moving to discussing about ortho projection. A projection P in a Hilbert space H is called ortho projection if P equal to P star. That is inner product of pxy equal to inner product of px and y equal to inner product of x and py for all x and y in H. Okay, a projection P in a Hilbert space H is called ortho projection if P equal to P star. That is inner product of Pxy equal to X into inner product of X and Py. Okay, this is the definition of an ortho projection. Now moving to property. If P is an ortho projection, then image P is orthogonal to kernel P. Okay, if P is an ortho projection, then image P is orthogonal to kernel P. Moving to proof, we know that if P is a projection, then P square equal to P and kernel P equal to image of Q, that is image of I minus P. So to prove image P is orthogonal to kernel P, it is enough to prove that inner product of z and w equal to 0 for every z belongs to image P and w belongs to kernel P. Okay, let z belongs to image P. That means there exists a x belongs to x such that px equal to z. Let w belongs to kernel P. That means w belongs to image of I minus P. That means there exists a y belongs to h such that I minus py equal to w. Okay. W belongs to kernel P implies we get there exists a y belongs to h such that I minus py equal to w. Now evaluate inner product of z and w. And this is same as inner product of px and I minus py. Clear? But P is a ortho projection. Inner product of Px and Y is equal to X into inner product of Py. So you can write this as inner product of X, comma, inner product of X and P into I minus Py. This is P minus P square Y. But P is a projection, therefore P square equal to P. That means this is 0 of Y and that's equal to 0. As x and y are arbitrary, we get inner product of zw equal to 0 for every z belongs to image P and w belongs to kernel P. This implies image P is orthogonal to kernel P. Clear? Okay. Therefore, if P is an ortho projection, then image P is orthogonal to kernel P. Moving to next result. If P is a projection satisfies the condition image P orthogonal to kernel P, then P equal to P star. Okay, that means if P is a projection which satisfies the condition image P orthogonal to kernel P, then P is a ortho projection. Clear? So given P is a projection, therefore P square equal to P. Also image P is orthogonal to kernel P implies inner product of X is orthogonal to Y for every X belongs to image P and Y belongs to kernel P. So first what we have to prove? We have to prove in P equal to P star. That is what we have to prove. Inner product of Px and Y equal to inner product of XPY for every X comma Y belongs to H. That is what we have to prove. Okay. So just recall one property that we have discussed in our last class. If E1 equal to image P, E2 equal to kernel P, then E equal to E1 plus E2. Okay, using this result for every x belongs to H, you can write as some x1 plus x2 where x1 belongs to E1, E1 is image P, E1 is image P, and E2 is kernel P. Okay. So for every x you can write like similarly here also image P and kernel P. Okay, y1 plus y2. So if x1 belongs to image P, what is the result we have? We have P x1 is equal to x1. If x1, x2 belongs to kernel P, what do we have? P x2 equal to 0. Similarly, P y1 equal to y1 and P y2 equal to 0. That we have. Okay. So given we can write x like this, y like this. Here given inner product E1 is orthogonal to E2. That means inner product of x1 and x2 equal to 0 because E1 the x1 belongs to E1, x2 belongs to E2. Similarly, inner product of y1 and x2 equal to 0 because y1 belongs to E1 and x2 belongs to E2. X1 y2 equal to 0. Similarly, inner product of y1 y2 equals 0. Now, what is inner product of pxy? By definition, px1 plus y1, y1 plus y2, p linear, px1 plus px2, okay? But px1 is, x1 belongs to p, px1 is x1 and py1 is y1. This is 0, px2 is 0, that means can write like this, but inner product of x1 y1 equal to 0, x1 y2 equal to 0, therefore this is equal to x1 y1. Now what is inner product of x and py? x1 plus x2 py1 plus y2, x1 plus s2 py1 plus py2, py1 is y1, py2 is 0. That means inner product of x1 plus x2 and y1. This is same as inner product of x1 y1 plus 0, which is equal to x1 y1. Thus we get inner product of py, x and py is equal to x1 y1 inner product. Here also x1 y1. From 1 and 2 we get inner product of pxy equal to inner product of x and py for every x comma y belongs to H. This implies p equal to p star, implies p is an ortho projection. Okay. Now moving to next property. Property 6.4.7. Every ortho projection P satisfies the condition 0 less than or equal to P less than or equal to I. Okay. So first we prove P greater than or equal to 0. Then we prove P less than or equal to I. Okay. So to prove P greater than or equal to 0, what we have to prove? We have to prove inner product of Pxx greater than or equal to 0. Now inner product of Pxx is equal to P you can replace by P square because P is a projection. P square x x. And P square you can write as inner product of P of Px x. And as P is an ortho projection, you can write this, take P here. That means because inner product Pxy equal to xpy by ortho projection. Okay, therefore this is px inner product, and this is norm of px square, which is greater than or equal to 0. Therefore, inner product px is greater than or equal to 0 for every x belongs to H. This implies p greater than or equal to 0. Now, to prove p less than or equal to I, it is enough to prove inner product of pxx less than or equal to inner product of ixx. So to prove p less than or equal to I, we have to prove this one. Okay. By 6.4.3 we have for every x belongs to H, we can write x is equal to px plus I minus px. Okay, for every x we can write as px plus I minus px. Therefore, norm of x square is equal to norm of px plus, this is actually this is also norm of px plus I minus px whole square. But here, as x and y are orthogonal, we get this is equal to norm of px square plus norm of I minus px square, because you can evaluate this norm of x plus, already we have discussed this, this is equal to norm of x square plus norm of y square if x and y are orthogonal. Okay. So using this result, because image P is orthogonal to image of I minus P. X is in, okay, so Px is in image P, I minus Px is in image of I minus P. So we get this result. Now from this, norm of Px square is equal to norm of x square minus I minus P, norm of I minus Px whole square. Norm of x positive, this is also positive, therefore clearly a positive quantity is subtracted from norm of x square. Therefore this is less than or equal to norm of x square. So norm of Px square less than or equal to norm of x square. Norm of Px is inner product of Px. Norm of x square is inner product x and x. And Px you can again write as here using P's ortho projection. P of Px x, and this is less than or equal to inner product of x. And this is P square x less than or equal to x. Px x less than or equal to this, you can write as xx, you can write as ix, okay, ix. This implies P less than or equal to I, implies P less, thus we get 0 less than or equal to P less than or equal to I. Okay, so that's all for today's class. In the next class we will discuss this result. Let EI equal to image PI, that is EI equal to PIH. If P1 P2 equal to 0, then P2 P1 equal to 0. E1 is orthogonal to E2 and P1 plus P2 is an ortho projection onto direct sum of E1 and E2. Okay.